Now, something that you're probably more familiar with is gravitational potential energy. And effectively, if we have a mass and we move it up inside that gravitational field, the higher you move it, the more gravitational potential energy it has. Until eventually, if you move it so far away from the surface of the planet, it eventually has zero potential energy. And this is very much a bit like gravitational potential that we've already seen. And effectively, this is defined as the work done to move a mass from infinity to a point in a gravitational field. And we can basically calculate this by saying E is equal to mvg. So last time, because effectively the gravitational potential was per unit mass, now we've just multiplied it by the mass to actually find the energy. And what is often maybe useful to think about isn't so much the actual total energy, but the change in energy as this moves around that field. And therefore we can say the change in energy is equal to m times the change in gravitational potential. And there are really two sorts of fields that we can consider. Now, the first type is a uniform field, like the kind of thing we have on the surface of the Earth. And basically, in order to increase the gravitational potential energy, what we've got to do is we've got to move that object higher in that field. So this is a bit like if you're walking around, if you're walking on a flat road, you don't increase your potential energy. It's only by going up a hill that that increases. The other kind is a radial field. And we already know that Vg is equal to minus Gm over r. And when we're talking about radial fields, we're kind of talking about the field that kind of really radiates from this object here that has mass. And we can basically then say that the energy is equal to m times Vg, which equals minus Gmm over r. And again, we can basically increase our energy in this field by increasing the radius. Now, perhaps you were some evil genius, perhaps, and you wanted to steal the moon and move it a different distance away from the Earth. Well, effectively, what we can look at is the force on the moon due to gravity at different distances when we look at the distance away from the centre of the Earth, which is going to be our distance of r. And effectively, what we want to do is we want to move that moon from A to point B. Okay, and as we do it, what we're going to do is we need some energy to actually get it from A to B. And effectively, what we can look at is, first of all, the force on the object, and the force has a relationship a bit like this from what we've seen with Newton's laws. And if we want to go from position A to position B, what we need to do is we need to input some energy. And basically, the area under a fourth distance graph is equal to the energy. And it's this area here, which is equal to the increase in gravitational potential energy of this object moving from A to B.